Okay, a very good morning to you all. We were discussing about some tutorial on the stability of the slopes. So yesterday we were discussing about how to solve the stability problem using the Morgenstern and Bishop method. So this is the statement of the sum and these are the solutions. So when you talk about the Morgenstern and Bishop method, so the form of the equation for determining the factor of safety, that is Fs, is m dash minus n dash into Ru, where Ru is the pore pressure coefficient. The value of it typically varies in the range from 0 to 0.5. So it could be higher than 0.5, but a majority of the cases they will consider up to the 0.5 only. Now, as for the Bishop and Morgenstern, they have given a lot of tables, which is giving the values to be picked up. Those are m dash and n dash, which are again a function of the other parameters like the pi dash, that is angle of internal friction, then c dash by gamma h, and d value. Since in the given statement of the sum there was no mention about the value of d, so therefore what we have done is we have taken all the three values of d, and corresponding to all the three we try to compute the value of the factor of safety, and whichever is giving or yielding the least factor of safety, that was considered as the factor of safety for that particular slope. So yesterday I have demonstrated how to pick up the value of the m dash and n dash from this table. So in the given sum, the slope angle has been given, that is 2 horizontal to 1 vertical. So this is 2 horizontal to 1 vertical. So this is fixed. Now in a next step, you need to determine the c dash by gamma h value, that is also equivalent to 0.05 as per the calculation. Now another parameter that you need to look into is what is the value of the pi dash. So here it is given in the sum as 25, and corresponding to 25 you try to pick up the values of the m dash and n dash for a given slope of 2 horizontal to 1 vertical. So 2 horizontal to 1 vertical. So for pi dash of 25, m dash is 1.624 and n dash is 1.338. So once m dash and n dash values are known, so we can able to determine the Fs with the help of the equation m dash minus n dash into Ru. Ru is given as 0.25. So this is very simple. So I also explained to you, suppose if exact value of the pi dash is not given in the sum. For example, here the pi dash is 25. If pi dash of 26 has been given, so you need to interpolate between 25 and 27.5 for the values of the m dash and n dash. Okay. So for three different values of the d, so three different factor of safety values were calculated, so which were 1.29, 1.423 and 1.667. Whichever is the least, so that will be the factor of safety value to be considered. So here in this case it is 1.29. Okay, so this is how you can able to utilize the method proposed by the Bishop and Morgenstern for the case of the steady state seepage condition. Now it is further modified by Spencer alone and Mikulovsky. So this is the Spencer solution. This also we did discuss. As for the Spencer, first you need to assume some initial value of the factor of safety assumed. So for the assumed value, you need to calculate the ratio of c dash by fs into gamma h. And for the calculated c dash by fs into gamma h, from the defined graphs which were given by the Spencer, you need to pick up the value of the pi dash d. Once pi dash d has been picked up from the graph, then you need to calculate the fs, that is fs calculated, which is the ratio of tan pi dash by tan pi dash d. Okay, so this exercise you need to do for several trials. So here in this case it has been done for 4 trials, and once 4 trials have been made, you need to develop a plot between Fs assumed versus Fs calculated as shown in this graph. Now, in order to pick up the value of the Fs corresponding to the strength of the soil material, that is Fs with respect to the strength. So draw from the horizon, so an inclined line with an inclination of the 45 degree. So wherever this line intersect the relationship between Fs assumed versus Fs calculated, that would be the factor of safety value for that slope under steady state CPS condition as per the Spencer method. Okay, just recall. So this is the second method. Now the third method proposed by Mikulovsky. So he also has given a lot of predefined charts. So here in this case, as for the Mikulovsky, it is Fs by tan pi dash on the vertical axis and C dash by gamma h into tan pi dash on the horizontal axis. Again, so different trend lines were given for different slope angles. Here you can see for beta is equal to 15, 30, 45, 60, 75 and 90. And for different values of the pore pressure coefficient. So this graph is valid for Ru is equals to 0.25. Now, if you look at this graph, you need to first calculate the ratio of C dash by gamma h into tan pi dash. So rest all the parameters has been given. So calculate C dash by gamma h into tan pi dash, which is equivalent to 0.107. While beta is 1 upon 2, that is 26. So corresponding to 0.107, maybe you need to draw a graph for 26 approximately, or here again you need to interpolate. Between beta is equal to 15 and beta is equal to 30. So based on the interpolation, so you get the ratio of Fs by tan pi dash. So here in this case, so it is calculated as 3.1. So now Fs by tan pi dash is nothing but 3.1. So I now already know from the statement that the sum pi dash is equal to 25. So only parameter to be calculated is Fs. So Fs is equal to 3.1 into tan 25, which is approximately 1.45. So this is how you can use all the three methods: the Spencer method, Mikulovsky's method, Morgenstern and Bishop method, for calculating the factor of safety of a slope subjected to steady state CPS condition. Now let us recall what are the values of the factor of safety determined from the three different methods. So the first method, Bishop and Morgenstern, this is 1.29. As for the Spencer method, it is 1.3. Okay. While as for the Mikulovsky, it is 1.45. So Spencer and Morgenstern method, they are almost equal, 1.29 and 1.3. While Mikulovsky method has given a slightly higher value of the 1.45. So if you are originally doing the factor of safety calculation, so in real life situations, you can in fact use all the three different methods, and whichever method is giving the least factor of safety value, that should be considered for all practical conditions. Okay, this is some kind of a guideline. Okay, so this is how you need to acquaint with different methods for calculating the factor of safety. Okay, now there is another condition, because all the previous discussion was pertinent to when a slope is subjected to steady state CPS condition. Okay, but what if the slope is subjected to another condition, something like a sudden drawdown? So this is typically possible in case of the canals or the reservoirs, where in the canal the water level initially at very high level. So here you can see at very high level, but in no period of time or any very short period of time. Now here, what do you mean by the short period of time? So the short period of time means, suppose if you take the soil mass between the top elevation and water lowered elevation. So this is the top elevation of water, and this is water level which has been lowered in a short period of time. And this is the soil mass. So this is the soil mass. So the condition for drawdown is such that the water within this soil doesn't have a sufficient time for dissipating the pore water pressure. So here we can recall the fundamentals of your permeability and the fundamentals of your consolidation theory. Okay, so when you are talking about the permeability or the consolidation, so the permeability is dependent upon the soil type. So usually for canals we try to use little impervious soils as a embankment material. So therefore you can assume that so the permeability of the embankment material will be lesser. So although not equivalent to that of a liner material, but it is reasonably so lesser value. So therefore with such low permeability value, so whenever you lower down the water, so the water within this soil volume will not dissipate in the amount of time which is required to lower down the water level from higher to the lower. Now as a result, what will happen if no water gets dissipated from this volume, so this becomes some additional weight in addition to the soil component. Now suppose if you do not design the stability of the slope accounting for such a condition, then because of this additional weight of water within the soil volume, the slope may fail. So this failure is called as a rapid drawdown condition. Okay, so here also it is approximately said that under drawdown condition, the gamma sat is approximately twice that of the gamma w, almost double that of the weight. So then you can imagine the weight is double and that weight is not accounted for in the stability. So then there is an obviously one can envisage some kind of the failure under drawdown condition. Okay, so this is the fundamentals of the drawdown condition. Now here there are two things. The two parameters, that is L and H, where H is the total height of the water at the initial condition, and where L is the height of the water that is lowered from higher elevation to the lower elevation, where beta is the slope angle. So for the case of the drawdown, Morgenstern has proposed an equation. So these again the Morgenstern has developed several predefined graphs as we can see in this slide. So Morgenstern's drawdown stability chart for C dash by gamma H is equal to 0.0125. So there are several graphs corresponding to C dash by gamma H of 0.0125, 0.05, 0.1, so on and so forth. Now if you look at an individual graph, so here 4 graphs have been given, but 4 refers to 4 different slope angles. So the very first one is beta is equals to off, that is 45 degree, and this is tan beta is equal to 1 by 4, and tan beta is equal to 1 by 3, and tan beta is equal to 1 by 5. So 1 by 2, 1 by 3, 1 by 4, and 1 by 5. So all the 4 will refer to 4 different slope angles. On the other hand, so the another parameter that is accounted for in the drawdown case is the pi dash value. Another parameter that is accounted for is L by H, because this is a variable parameter. We do not know what is the level of water that is lowered from top to the bottom elevation. So this might vary from case to case. So therefore it should be a function. So therefore they have taken L by H as one of the function. Then ultimately your target aim is to pick up or determine the factor of safety value. If this is the lower down water level, and if this is the soil property, and if this is the geometrical property, what would be the factor of safety? So you look at, so it is covering almost everything. So L by H is geometrical parameter, tan beta is a geometrical parameter, pi dash is a soil property, while Fs is the overall behavior. So Fs here embedded by default embeds the geometrical parameter and the soil parameter. So therefore it is overall behavior of the soil mass. So in the previous slide, it was belongs to C dash by gamma h is equal to 0.0125. Now, so this bunch of sats represents to C dash by gamma h is equals to 0.025. Now again, I repeat. So for any intermediate value of C dash by gamma h, see for example, this slide. So here it is 0.0125. So here it is 0.025. So how do we calculate the Fs value if it is C dash by gamma h is equals to 0.02? So again, same thing. You need to do the linear interpolation. There is no other goal. Linear interpolation. Now this is for C dash by gamma h is equals to 0.05 and 0.025. 0.05. Yeah. So he has given up to C dash by gamma h is equals to 0, 0.0125, 0.025 and 0.05. Okay. So I hope you should not be having any kind of a confusion. So where to use and how to use these graphs, especially to determine the factor of safety value for a slope subjected to the sudden drawdown condition. Anybody has any question? Anyone?
Sir, this graph is only valid up to 10 beta is equal to 1 by 5.
Yeah, but 1 by 5 is how much it will be? It is more than 70 or 80. See,
Yes, sir.
tan beta is equal to 44. 1 by 2 is 44.
Mm,
1 by 3 is how much?
16.
60. And 1 by 4 is, I think,
Sir, 1
74.
by 5 is 11.4, sir.
11.4. Okay. See, very, very gentle slope. So, such slopes are rare to use it. We maximum use 1 by 2 or 1 by 3. Or 1 is 1 also. A very steep slope. Very gentle slope and very steep slope. Good. Any other question?
Sir, they are given for 11 to 26, not up to, not above the 26, sir.
Okay.
1 by 2 is, sir, 26. 1
26.
by 4 is 14.
14. Fine, fine. No problem. So, they have given from 11 to 26. Good. So, any other questions from anybody? Savi or Binish?
No, sir, clear.
Okay, very good. Yashwant?
No, sir.
Okay, very good. So, let us go to the another example. So, this all we have discussed.
Sir, in real example, like sudden breakdown of statuses happen. That's why this sudden drawdown case happen.
Yeah, yeah. In real life, there are several cases also reported. Okay. So, in fact, the development of all these theories has evolved after seeing the failure conditions. Okay. So, I request everyone to note down this sum. Okay, so I request everyone, so please note down this sum and start solving it. So a slope cut to 1.5 horizontal to 1 vertical will be made in a shale rock stratum that has bedding planes that have an apparent dip of 16 degree. So that is shown in the figure. If the acceptable factor of safety against failure is at least 2 along the lowest most bedding plane, is this slope stable? So use a unit weight of 20.1 kilonewton per cubic meter and bedding strength parameters of C 22 kilopascals and pi 30 degree. So here both the things have been given. If you look at carefully, the angle made by the failure plane is 16 degree, while the slope angle is tan 1 divided by 1.5. So 1 vertical to 1.5 horizontal. The height of the slope is 20 meter and the horizontal length of the slope is 85 meter. So anybody can tell me the solution? Hello? So any suggestion on how to go about this problem? Vishal?
Sir,
Yeah. Any idea? Ashwant, Savi, Dinesh? Okay, so I will give you a small idea.
sir, we can,
Yeah, tell me, Vishal.
sir, like we can do like a driving force and resistive force.
Exactly.
We can compare with the factor of safety with true if it is If it is satisfied, then it is correct, stable, or if it is not satisfied, then it is not stable, sir.
Yeah, very good. So in that manner we have to go. So as we know from the fundamentals, the factor of safety is nothing but a resisting moment by the driving moment, or resisting force by the driving force. So here, where is the resisting force or the resisting moment? In fact, resisting force. So from where the resisting force is coming, and from where the driving force is coming here.
Sir, resistance force is coming along the bedding plane.
Yeah, so all along the bedding plane, so over the length of approximately 85 meter. So this is the resisting force. So how do we calculate the resisting force? So that is tau is equals to C plus sigma tan pi. Okay, C plus sigma tan pi. So now here C I know, pi I know. So sigma, that is weight of the soil or the normal component of the soil, that I need to calculate. This is the resisting force. Driving force is nothing but, so the total weight of this one. The total weight of this one. So somehow, based on the triangles, if you can able to calculate the weight of this component and divided by the tau, then what you get is the factor of safety value. Okay, so this is how you need to go about this one. Okay, so let me show the solution. So first, the triangle of a rock above the potential slip surface as a weight W per unit weight. So that I told you. So which is nothing but the same W is causing the driving moment. So therefore W can be calculated. This is an approximate solution, not exact. If you take the triangle, so W, the weight of the component is nothing but area multiplied by the density. So where gamma is 20.1 kilonewton per cubic meter. So area of the triangle of base into height. So of the base width is 85 meter. Then the height approximately given is 11.3 meter. So therefore what you get W is
Sir,
9650. Yeah.
sir, 85 is the horizontal distance, not inclined distance, no, sir.
Yeah, true.
So we have to
Ah,
convert it to L, no, sir. We have
ah,
angle also, sir.
that's why I told you, this is approximate. See, there are two things. Suppose if you want to convert 85, that is L in the form of inclined, then again you need to determine the inclined height. The vertical height is 11.3 meter. So here you need to determine the inclined height. Did you understand, Vishal? So your
Yes,
analogy
sir.
is correct. Your analogy is correct, but you need to determine the inclined height. So one parameter is unknown. Either I do not know the inclined height of this one, or I do not know the inclined length of the base. One parameter is unknown. So anyhow you are compromising. So therefore this is an approximate solution. So this is an approximate solution. Okay, so try to understand the fundamental, how it has been solved. So now approximately I have taken the triangle of base into height multiplied by the density. This is 9650 kilonewton per meter. So then this is the length of the slip plane, that is 88.4. So if you want to take 88.4 as inclined length, so you may have to increase the height from 11.3 to, it may be 12 or it may be 11.5 or something, whatever it is. So if you can able to calculate that inclined height, that is the plane normal to the inclined line, it is excellent. So I also encourage everyone to calculate the inclined length as well as the normal height, the perpendicular height. You can still do it. Okay. Then inclined length is 85 by cos 60. So that is 88.4 meter inclined length. So then we know the factor of safety equation, that is a resisting force by the driving force. Resisting force can be calculated as tau divided by the driving force, that is the weight component. Weight component. So your tau is nothing but C plus sigma dash tan pi. So C is only the one component. So you need to multiply for the total resisting force with L. So C into L plus W cos alpha. So this is normal component of the weight multiplied by tan pi divided by the tangential component of the weight, that is W sin pi. So I know the W, I know the length, I know the C, so I know the alpha. So substitute in this equation and try to calculate the factor of safety value Fs, which is 2.7, which is greater than 2, therefore okay. So if anybody has any question, please raise right now. I believe it is clear to everyone how to calculate the factor of safety. So based on the weight calculations of a slope.
Sir,
Yeah.
sir, I have some difficulty, sir. Sir, they mentioned factor safety at least two, sir. But we
Yeah.
know that in general, factor safety more than one means stable or verge of failure, sir.
Correct.
At at one, sir, verge of failure and more than one, it is stable, sir. And
Yeah.
they asked to have at least two factor safety, sir. Then it is not a stable condition.
No, no. It is their requirement. I can have my own requirement. See, the number seems to be very tricky. You may think that the factor of safety I can have a 2. But to arrive at the 2, you need to change whole lot of geometry of the slope. It is not so easy. Okay. Uh, Even suppose if you imagine that your factor of safety that you are getting is 1.9. And in reality, if I want to enhance the factor of safety from 1.9 to 2, the best thing that I need to do is enhance or increase my geometry of the slope. But on the paper, I can simply increase it. But in reality, so that much volume of the soil has to brought from somewhere to construct the slope. And this bringing and hauling the soil, everything is a cost intensive. You understand?
Yes, sir.
Okay,
Yes, sir.
so even if you move from point one factor of safety, so everything has some kind of the cost incurrence. So that also need to be taken into account. And moreover, depending upon the condition, so we fix the values of the factor of safety. Suppose here, why did they say the minimum requirement is 2? Because this is in view of two contrasting materials. One is the soil, next is the rock. So there is, even if there is a slight triggering of the movement, so then there will be whole collapse. While such may not be the case in case of a homogeneous material like a soil, because that is a progressive failure. While there are two contrasting materials, so because of the contrast in their properties, they will accelerate the failure. That is why normally wherever there are two contrasting materials are there, we normally consider higher factor of safety value. Is it clear now?
Yes, sir. Yes,
Good.
sir.
Good, good. Now extend the same problem. Suppose if there is a steady state C phase parallel to the slope, parallel to the slope. So then try to calculate what would be the reduction in factor of safety value. What would be the reduction in factor of safety value? So in fact, same repetition of the previous sum. However, when you try to calculate, so is there any change in the driving force component?
No, sir.
Okay. So where is the change?
In weight parameter, sir.
Yeah. So that is resisting parameter. Now it is understood by now everyone that suppose if there is a steady state seepage, so first of all the interface between the rock and the soil is in a fully saturated condition. Whenever there is a water steady state seepage, this seepage force is against the shear strength direction. So therefore, so the seepage, the developing shear strength must also counteract not only the normal component of the weight of the soil. It also should counteract the seepage force. So therefore, so in the presence of the steady state seepage, it is obvious that the decrease in the shear strength causes decrease in the factor of safety value. So this is the very fundamental crux. So when you try to solve the factor of safety problem, okay, same shear strength has to counteract two components. One is the weight of the soil, next is the seepage force. So therefore, so it causes reduction in the factor of safety value. Okay, so let's see the solution. The weight W, it is remains same, and the length of the slip plane, that is 88.4 meter. But what additional parameter comes into the picture, that is the pore water pressure is based on an estimate of its value along the length well. So it is given that the water level can rise from the bedding plane up to 3.2 meter conservatively. So this is also mentioned here. If you look at here, so it is 3.2 meter. So meaning thereby, suppose if I put at this point my piezometer or my manometer, the water level rise is approximately 3.2 meter. 3.2 meter. So how do I calculate U, which is nothing but your gamma W into H, where H is nothing but 3.2 meter. So you know that sigma dash is equals to sigma minus U. Sigma minus U. So sigma we have calculated in the previous sum. Now the additional term that comes into the picture is U, that is pore pressure component. So sigma dash is equals to sigma minus U. So this is how you need to account for the development of the pore pressure component. So in the calculation of the factors. So here the water level rise is up to approximately 3.2 meter. So U is equals to gamma W into Z. So gamma W is 9.81 and the height of water rise is 3.2 meter. So therefore the total U component is 31.4 kilopascal. So we know the equation for factor of safety, which is nothing but resisting force divided by the driving force. So C dash into L plus W cos alpha. Now this is sigma dash. So sigma minus U component also comes into the picture. So that is U into tan pi divided by W sin alpha. So this is a tangential component. So C dash is 15. Substitute all the values. So 15 multiplied by 88 plus 9650 into cos 16 minus U, that is 31.4. So divided by the driving force, that is W sin alpha. So now, so if you simplify, what to get the factor of safety is 1.76, which is less than 2. So therefore not acceptable. So the computed factor of safety of 1.76 is less than the minimum acceptable value of the 2. So therefore, so this design is not acceptable. So notice that a rising water table decreases the stability of the slope. Now how?
Sir,
So yeah.
sir, this is wrong, sir. See, na, units are kilonewton per meter, and here U is kilopascal, sir. How do we minus?
Kilo. Then you need to multiply this with the L.
Yes, sir. It need to
88.
multiply 31.4 into L, sir.
Okay. Yeah, this is kilonewton per square meter, and this is kilonewton per meter. Yeah. So this should be multiplied with. So 31.84. That's what I'm also thinking. So this should be multiplied with 88.4. So then this will become so kilonewton per meter. So this is also kilonewton per meter. This is also kilonewton per meter. Yeah, fine. Very good. So this will further reduce.
And also, sir, we have to divide by 2 because we are finding the triangle area, sir.
No. For you, it is not required. It is a single component.
Okay, sir. So to find U, we don't have to find the area of that plane, like half into U gamma H into L.
No. That is just to determine the weight of the soil. Suppose if you multiply half gamma into H, then you are calculating the weight of the water.
Yes, sir. But here, sir, we will multiply the like L.
No, this is CPS force you are calculating, na?
Yes,
Not
sir.
the weight of the water.
Yes, sir. Here we will multiply L, na, sir?
Multiply N. So
Okay.
otherwise you are not matching the units. So it will be approximately how much? The final factor of safety value.
Sir, 1.39.
Okay, 1.39. Others may please check and confirm. So 1.39.
Yes, sir. Same 1.39.
Very good. 1.39. Okay. So this is how you need to calculate the factor of safety. Suppose if the direct data has been given or based on the weight calculations, whatever it is. Okay, now let us go to another sum. Just note down this sum. So in fact, the same sum I request everyone to repeat using the graph paper at your home. So till now, what we have done is we try to calculate the factor of safety based on the mass movement equilibrium equation. But now go for another sum that is based on the method of the slices. So in reality, you cannot directly use the manual methods for calculating the factor of safety for method of the slices because it is very laborious. But just for an example sake, I'm showing one of the example here so that you can understand. That understanding is required because when you operate any kind of a software, so there are more than 2 dozen numbers of the softwares are available to calculate the factor of safety. Almost every software or every method so is taken into account only the method of the slices. Only few other softwares are available which are based on the mass movement, but majority of the softwares are based on the method of the slices. So a 30 feet tall 1.5 horizontal to 1 vertical slope is to be built as shown below. The soil is homogeneous with C dash 400 pound per square feet and pi dash 29. The unit weight is 119 PCF, that is pound per cubic feet above the groundwater table, and 123 pound per cubic feet below the groundwater table. So using the ordinary method of the slices, compute the factor of safety along the trail circle. So in fact, so in the sum itself, they have divided the entire the slope, entire the area within the trail slip circle failure into so many number of slices. So 1, 2, 3, 4, 5, 6, 7. Now you can also notice that either we can make the slices of uniform width or non-uniform width, it doesn't matter. So here, just for the sake of understanding, so they made a non-uniform width of the slices, doesn't matter. Next, most important thing is that if you look at the angle made by the failure plane at different locations are corresponding to different slices. So it is both positive and negative. Suppose if you look at the slice number 1, the angle made by the failure plane is negative. It is not the positive. Meaning thereby, you can presume that slice number 3, 4, 5, 6 and 7 are the driving forces while 1 and 2 are counteracting the force coming from the 3 to 7 number of slices, because their angle of inclination is negative. It is a negative angle, it is not the positive angle. So positive indicates the driving moment, the negative indicates the resisting moment. The resisting moment. So this is the reason the method of the slices has gained more importance than the mass movement, where we have treated that the whole mass of the soil is acting as a driving force, but which is not true in reality, and the same thing is demonstrated in this slide. So here the angle, so this one is approximately 18 degree. Okay, so when I say alpha is minus 18, so it is presumed that it is not a circle, rather it is a approximate straight line. Approximate straight line. Okay. So this alpha. So alpha is equal to minus 18, minus 7, 8, 24, 38, 53, 67. And as we know, corresponding to each slice, we should aware what is the weight of this slice. Unless we know the weight of this slice, we can't able to determine the factor of safety. Okay, so the first thing you need to know is how shall I calculate the weight of the each slice. For that purpose, I need to know the gamma and I need to know the area. So gamma of the soil above the water table is 119 pound per cubic feet and below is 123 pound per cubic feet. The second thing is, how do I calculate the area? How do I calculate the area? For calculating the area, I know the width of the slice, width of the each slice. Now I need to know what is the height of the each slice. What is the height of each slice? So this height can be determined if you redraw or reproduce this entire slope on your graph sheet. So that's why. So I encourage everyone, reproduce the same graph as it is on your graph paper and try to calculate the area of the each slice and multiply that area with the density. Thereby you get the total weight of the respective slice. It is very simple, very simple. But that reinforces your fundamentals. So that reinforces your concepts on how to calculate the weight or how the software calculates the weight. Because if you give it to software, in no minute the software does measure what is the height of the each slice, and it calculates the area and thereby multiplies with the gamma and thereby gives the height. So for calculator, it's a fraction of seconds time. But for us, you need to manually measure the height of the each slice. And if you look at the other thing, for example, if you look at the slice number 3, a part of the slice is above the water table and part of the slice is below the water table. That means you need to calculate two different weights. The same thing to be repeated for 4, 5, 6. 7, it is completely out of the water table location above. And now let us see how they have done it. So first, the solution weights W1 by B. The B is the width of the slice. So W1 means the weight. So here this is half base into height. Half base into height. So 10.8 is the width. Height is 10.3. So this 10.3 is nothing but this 10.3. So this height. Height of this side. Height of this side. So half base into height. Half base into height multiplied by density, that is 119. So that will give me the weight of this slice. Weight of this, that is 6620 pound per feet. Next, repeat for slice number 2. Slice number 2. But for slice number 2, a small portion of the slice is below the water table. Below the water table. Okay, so that also need to be accounted for. So therefore, 9.4, that is width. This is 10.3 on one side and 12.5 on the another side. That 12.5 is this side. So this is 12.5. This is 12.5. And this is 5.2. And this is 5.2. So width is remaining same 9.4. But density varies. 119 above the water table, 123 below the water table. So therefore, simplify everything. Then what you will get is the weight of the slice number 2. So repeat the same procedure for slice number 3, slice number 4, 5, 6 and 7.
Sir,
Yeah.
but for the second part below the water table, it is not 9.4, no, sir. It should be less than 9.4.
Yeah, less than 9.4. Maybe you can take half of 9.4. So here instead of 9.4, you may take half of it. 9.4. So for remaining components, W1 to W7.
Sir,
Yeah.
when we'll draw on the graph, sir, how do we know where it is water table from what distance?
You draw approximately, na?
Yes, sir.
So it is entering at the bottom of the slice number 6 and exiting at the middle of the slice number 2. And
Okay, sir.
you try to approximately connect it, so there is no problem.
Sir, in 2, the portion above the ground surface is not really trapezoidal, no, sir? We are using a
Uh,
trapezium formula. It
yeah, yeah,
isn't really trapezoidal.
that is true. But it is an approximate. Na? That's why the best thing is you try to redraw everything on the graph sheet, and based on that pockets, you can calculate the area. Or in that case, you can exactly measure what is the height on each side.
That means, sir, if we consider very, very lesser width, then it will be more accurate.
More accurate. Correct. Okay. Can I go to next slide? Okay. Now let's see how they have calculated the pore pressure parameter. So on slice number 1, no pore pressure parameter, that is U is 0. And on 2, so this is approximate height is 5.2 multiplied by the density, that is 62.4. So same repetition. So U3 on one side 5.2, on another side 10. So this divided by this, say average height. Average height multiplied by the width. So in fact it is height only. So here we don't need to consider the width of the slice. So U is equal to gamma W into H, only height. So this is average height.
Sir, why they have divided by 2?
Average height. Suppose if you look at slice number 3 na, so this side is 5.2.
But
So
sir, this
this side
same
is
thing we
5.2.
haven't done in the next question, sir.
See here you are calculating the height of the water. Don't get confused. U is equals to gamma W into H. Okay, how do you calculate the H? That's it. Earlier you are calculating the area and volume. So here you neither need to calculate the volume, neither need to calculate the area. You need to take the average height of water within the slice 3 at this point.
Okay, sir.
Okay, so this is how U3, U4, U6 and U7. So U1 and U7 no water table, therefore pore pressure is 0. Then finally you try to make some tabular form. Slice number, weight of the each slice, angle made by the failure plane, C dash value which is given in the sum, pi dash which is again given in the sum, the developing pore water pressure U, and the length of each slice, then the final resisting moment, that is C dash L plus WB by cos alpha minus WA, that is sigma dash minus U into tan pi dash. And ultimately the last column is the driving force, that is W by D.
Sir,
Yeah.
sir, here the formula should be W by B minus UL, then cos alpha, na sir? Cos alpha should be common
Ah,
for both.
it is cos alpha, no, cos W by B into cos alpha minus UL.
Sir,
Tan,
in the previous question we have taken W by B minus UL into cos alpha, sir. Cos alpha is outside. See, sir.
see, W cos alpha is multiplied with only W. W cos alpha. Okay. In fact, this is a little wrong. So cos alpha should be multiplied with only weight component.
Yes, sir.
Yeah.
Only
So
different in bracket, sir.
yeah. So some typographical error. Okay. So you need to make this kind of a table. This is shear strength component, that is resisting moment, and the last one is
Last one would be W by B sin alpha, na sir?
this is sin alpha, correct? W by V sin alpha. So many. W by D sin alpha. Okay, so at the end, take the summation of everything. So once this is known, now factor of safety is nothing but, so this divided by this, that's it.
Sir, here we can say the negative alpha is affecting only driving force.
Uh, yeah, it will affect only driving force. No?
Yes, sir.
And see, logically also it should affect only driving force. It should be eliminated from the driving force.
Sir, then it is good, na, sir, because that minimize the driving force. See, it is minus 3900.
It is good.
They're
That,
reducing the driving moment.
that's what I also told initially. And that is the merit of the method of the slices, which was grossly ignored in case of the mass procedures.
Yes, sir.
So this is the final
Sir,
fact of, yeah.
sir, hello,
Yeah.
sir, sir. have another sir.
Okay, anyhow, this is done. So you simply do it. So what you get is factor of safety. Okay, so I'm also giving this one, it is recorded. So you try to solve this problem also, another one. So just see the recording and try to solve this problem using the same method of the slices. Okay, so I will stop it here.
Thank you, sir.
Yeah.